Welcome back. This is the first chapter 3 video for the EE111 Lecture Series. And in this video, we're going to be talking about series and parallel resistors and how to combine series and parallel resistor combinations. So we're going to start with the series resistors. So in this image, you have a voltage supply, and that voltage supply is connected to a collection of resistors. These resistors are said to be in series, and what that means is, and we've talked about it a little bit in previous videos, what series means is that there's no way for the current flowing out of one component to do anything but fully enter another component. It means two components that share a node with nothing else connected, and what that nothing else connected means is there's no way for current to branch off anywhere else. So essentially, we have this current IS flowing through here, and whatever current IS flows through resistor R1 has to be the same current that flows through resistor R2 because there's nothing connected here, right? There's nowhere for the current to go other than if it exits, whatever current exits R1 has to enter R2. And the same thing goes for the rest, right? Whatever exits R2 has to go through R3, whatever exits R3 has to go through R4, and so on. So these are said to be series connected resistors. And we'll usually describe this as all of these resistors are in series in the sense that they are a string of resistors that are connected in such a way that the same current has to flow through all of them. That is to say, at each of their connection points, there's nothing else connected where current could branch off. And so this occurs quite often in circuits where we have things connected in series. This can be things like, in addition to resistors, you could have voltage supplies, current supplies, you could have all sorts of things that are connected in a series combination. But for right now, we're just going to focus on resistors. So in this image, we have 7 resistors connected in series. And let's do a Kirchhoff's voltage law equation. So let's do this around this loop. We already have labeled here, it's sort of hard to see, but we have IS as this labeled current through the loop. And this is going to be the same current for all of these resistors. So the Kirchhoff's voltage law equation would be starting here, working our way around the circuit, we're going to add the voltage drops. So initially we go up Vs volts, so that's a voltage drop of negative Vs. And then we have the voltage drop across R1 here. That voltage drop is going to be Is by Ohm's law. That's going to be Is times R1. And then across R2, it's going to be Is times R2. And so on. You can see that's going to be the same for all of these. So let's just keep adding these out. It's like I should have had maybe just 4 resistors or something because it's getting a little tedious. Okay. And all of that has to equal 0. Okay, so that's our Kirchhoff's voltage law equation around this loop. And you'll notice the only variables in this equation is Vs, which is known, Is, which is unknown, and these resistor values. So if we know these resistor values, we could solve for Is just using this equation, something to keep in mind. Okay, so taking this same collection, we just basically, if we take our equation we had on the previous slide, if we take this equation and this part here, which is just Is times a bunch of resistor coefficients, let's factor out that Is. So we're just going to factor that out, and then we have Vs, and we flip Vs over to the other side of the equation as well, and we have Vs equals Is times this sum of resistor values. Now, does this look like an equation you're familiar with? This equation is V equals I times something. What does that look like? That looks a lot like Ohm's law, and in fact, it's identical to Ohm's law, except instead of a single resistance here, we have this sum of resistances. And that sum of resistances is what we call the equivalent resistance for a circuit like this. That is to say that these resistors connected in series behave as a single resistor with a resistor value that is the sum of these resistances. So functionally, as far as this voltage supply is concerned, it doesn't care if it's connected to 7 resistors that have all these resistances, or if it's connected to a single resistor with an equivalent resistance, which is the sum of these resistances. And we can formalize this. We can formalize this by saying that whenever we have a series combination of resistors, we can say the equivalent resistance of that series combination of resistors is the sum of resistor values. And one thing that is quite commonly used in electrical engineering analysis, in circuit analysis, is this idea of the black box. So the black box is just a way of thinking about a system. It's a way of, when you're given a lot of information about a system, quite often you want to simplify that system as much as you can. And one helpful way to simplify that system is to say, let's pretend my system is in a black box. Let's pretend it's in a black box and we have two terminals sticking out of that black box. And all we care about is how does something external to the black box interact with that black box? So basically, if I'm something external to this black box, what does this feel like? What does this system that's in the black box feel like? Knowing nothing about what this system that's in there, what would any external system think it is? And in fact, if we think about it this way, we can basically say that this single resistor REQ being in the black box is identical to this collection of resistors in series. And it is helpful. The black box, the concept of the black box, is really just a logical exercise, a way of saying, do I care that this is 7 resistors? Because if I don't care if it's 7 resistors and I can treat it as if it's 1 resistor, I'd rather just treat it as if it's 1 resistor. And there are times when that's in fact the case. There are times when you're not interested in what the voltage is across R3, right? If you were interested in what's the voltage across R3, then yeah, you wouldn't want to just combine a bunch of resistors and get rid of R3 and just have this equivalent resistance. Or maybe you would and you want to undo it later on. But if all you care about is, for instance, what current is flowing through a voltage supply, and that voltage supply is connected to a collection of resistors, then yeah, this is a very reasonable thing to do, to combine into an equivalent resistance. So you'll see this concept of the black box, and you'll see me mention a lot, pretend this is in a black box. What do you feel? What do you perceive as being in that black box, not actually knowing what sort of combination or collection of things is in there? So series resistors, and some of you probably remember this from physics. Resistors in series behave as an equivalent resistance, which is the sum of those resistor values. Let's look now at parallel resistors. So we have an example circuit here, similar to the last one, but thankfully there's only 4 resistors in this example circuit. So my equation will be a little shorter. So these resistors are said to be in parallel. In parallel means they share the same voltage across their terminals. So in series meant they had the same current flow through them. In parallel means they share the same voltage across their terminals. And in fact, you can see in this circuit, this is just one node and this is just one node. So all of these resistors share the same 2 terminals. And if they share the same 2 terminals, they have to have the same voltage across them. So that's what parallel means. Parallel is things that share 2 terminals, regardless of whether or not other stuff's connected to those terminals. If things share 2 terminals, they are said to be in parallel, meaning by saying they share 2 terminals, we're just saying they have the same voltage. They must have the same voltage across them. Okay, now to analyze this, to sort of see how resistors in parallel behave, let's do a Kirchhoff's current law equation here. So Kirchhoff's current law equation, we'll do Kirchhoff's current law equation at this node up here. It's getting a little messy here, so let's, oops. So we'll do a KCL at this node here. And what do we do for KCL? For KCL, we do sum of the currents flowing out of this node equals 0. And we could do the sum flowing in equals 0, and we could do the current flowing out equals current flowing in. I like to, even at this early juncture, just start with, just write the sum of the currents flowing out. Be consistent with it, and you're less likely to make mistakes later on. So what's this current flowing out this way? Well, we labeled IS as flowing this way, so the current flowing out the other way is actually going to be negative IS. We'll probably see that flip over to the other side of the equation here sooner rather than later, but we'll see how it goes. So we have negative IS flowing out to the left, and then flowing down through this resistor. What's the current flowing through this resistor? Well, we don't know. It's not labeled. But we do know the voltage across this resistor, and it's Vs. And we do know this resistance, which is R1. So by Ohm's law, we can determine the current. What's the current by Ohm's law? Current, V equals IR, so I is V divided by R. So we can say the current flowing down here is going to be Vs divided by R1. And then same for R2. For R2, it's going to be Vs divided by R2. And then for R3, Vs divided by R3. And then for R4, Vs divided by R4, and all of that equals 0. So right now, we can write this. Let me look at peek ahead really quick. Yep, let's not do any more math on this page because I have it all done on the next slide. So, but once again, though, we're going to factor this VS out. So we're going to factor out these VS's. So if we factor these out, we're going to have VS times this 1 over R1 plus 1 over R2. And that's, in fact, what we get. So this is our equation on the previous page where there goes that IS. We had a negative IS and we flopped it over to the other side of the equation. So we have IS equals V times 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. That's not quite, in the previous example in series, we said, oh, we have V equals I times something. You know that equation. Well, now we have I equals V times something, which is that's not quite Ohm's law. So we can massage this into something a little closer to Ohm's law. So we have IS equals VS times something. So if we want to rewrite that, we could say, so basically dividing both sides by 1 over R1 plus 1 over R2, etc. Same thing over here. This is going to be a mess, I can tell already. Anyway, dividing both sides of this equation by that 1 over R1 plus 1 over R2 plus 1 over R3, then we get VS equals IS times 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, all to the negative 1. So now we have here, this is our equivalent resistance, or this is in our V equals I times something. What we're saying is that this system behaves as a single resistor whose resistance is the inverse of the sum of the inverses of these resistor values. And if you say, well, the inverse of the sum of the inverses, that's just the sum of the resistances, right? If you say that, you got to go back and study some of your high school algebra, because it's not, right? You can't. It's not. But I do stuff like that all the time. I will forget these massive mathematical concepts. When I took the SAT test, I remember I was sitting there and I had completely forgotten how to multiply two fractions. I had two fractions, and I was like, wait, multiply fractions. Do you add the numerator and multiply the denominator? I don't know. It's embarrassing. It's not. I mean, I passed the class. I'm good, but sometimes you have these weird moments where you just kind of forget these things that you spent years and years focusing on, and that's okay. But it's always don't let that mistake trickle on through. I mean, I ended up recognizing how to multiply fractions before the SAT test was over, and I did okay. But sometimes you forget these big things, and this is a big one. So you cannot distribute the inverse across addition. So, but okay. Anyway, so basically, in parallel, equivalent resistance is the inverse of the sum of the inverses of those resistances. And one thing we mentioned earlier, conductance, right? Conductance is the inverse of resistance. So this is a case where people tend to use conductances, because instead of taking the inverse of the sum of the inverses, that's basically just saying the sum of the conductances. So if you are working with a lot of resistances in parallel, sometimes it's more common to look at the conductance, because you can just combine all those components by just taking the sum of the conductances. So now, when is the time you have lots of things in parallel? For instance, the electrical system of a house. So all the outlet plugs in your house, well, at least all of them on one circuit, those are all in parallel. And that makes sense, right? Because you have the same things in parallel, you have the same voltage across them. So you have the same 120 volts AC across every single device you plug into those outlets. So when you're talking about devices plugging into an outlet, it might be more useful to think of the conductance of the device. Because then when you have multiple devices, like if you're me and you're cooking something, you're using that air fryer. Oh, I love those air fryers. You got to get one of those air fryers if you don't have one. So you're using your air fryer, and you got your toaster going, and you got your blender going because you're making a smoothie. All three of those things are going to be connected to the same circuit, probably in parallel. And if you want to make it easy, instead of adding the sum of the inverses, instead of taking the inverse of the sum of the inverses of resistance, you could just add up the conductances and say, oh, this is the conductance of all the things that are plugged into my kitchen outlets while I'm cooking dinner. So that is one time people tend to use conductance, but we don't do that enough to make it worthwhile. There are industries where they are frequently doing things like that, like imagining different appliances plugged into plugs, and there they might use conductance. But for us, you're just going to take the inverse of the sum of the inverses, and there's not really, that's all we're going to do. Because you would have had to do the same thing anyway. You would have had to take the inverse to find the conductance, and then once you added it up, you would have had to take the inverse to find the resistance again. So you're going to do the same work of taking the inverse and then taking the inverse of all the sums. But so it doesn't really save you that much effort to go with conductance, but this is an area where people tend to use it. One feature of things in parallel, though, that I want to mention is one quick check you can do. It doesn't make sure you did it right, but it verifies that you didn't for sure do it wrong, is whenever you're combining resistances in parallel, the equivalent resistance should always be less than the smallest resistance of any of the elements that were there. So if you had a 1 ohm resistor in parallel with 100, in parallel with 1,000, in parallel with 1,000,000, the total resistance in parallel is going to have to be less than 1. And that makes sense logically, because logically when you connect things in parallel, you're giving more pathways for charges to flow. You're always going to be decreasing resistance from your lowest resistor value because you've added extra pathways for charge carriers to flow. So it makes intuitive sense, but it also mathematically, it's a good way to check your work. So if you are taking a quiz or a midterm, and there's a question that says, combine these, and you have to combine these in parallel, I tend to be, much less forgiving if somebody gets the wrong answer and their equivalent resistance in parallel was actually higher than one of the resistors in that combination, because they should have easily been able to recognize. There's no, if you get the math wrong, whatever, that's your math teacher's problem. I mean, you should get the math right, but I mean, the primary goal of my class, primary goal for me, for you, is to understand these concepts and techniques, not to fat finger a button on your calculator or something like that. But if you do fat finger a button on your calculator and you find an equivalent resistance that is higher than one of these resistors that in this parallel combination, then I tend to be less forgiving, because you really should have recognized that. You should have seen immediately. There's no way for the resistance to go up by adding extra pathways in parallel. So something to check. Be careful about that. The book has a little shortcut. So this is kind of cumbersome, this inverse of the sum of the inverses. I'm going to write this wherever space I can. The book has a shortcut for two resistors. If you have two resistors, R1 in parallel with R2, and the sort of two backslash lines is the way people tend to show resistors in parallel when writing them quickly. You can write the equivalent resistance as R1 times R2 divided by R1 plus R2. And that's a nice quick way of writing the equivalent resistance of two resistors in parallel. Why do I not like this, and why do I try not to write it in the slides? The book likes to focus on it. The book loves it and wants you to use it. What I found, though, is a lot of students incorrectly assume that this shortcut means that if you have three resistors, say you have R3 in parallel with R1 in parallel with R2, that you can just continue the trend, that you can just do R3 and then plus R3. You cannot do that. So you cannot, it's not, the equivalent resistance of resistors in parallel is not the product of the resistances divided by the sum of the resistances. That's only true for two resistors in parallel. If you do three, there's no shortcut. There's no shortcut. And because of that, I don't even like to mention the shortcut in the first place. And I dropped my pen, so if I don't edit this out, I gotta pick my pen back up. All right, there we are. Okay, so there is a shortcut for two. It only works for two. Don't make the mistake. I've seen so many students think it's a rule for 3 and 4 and try to use that equation, try to use that form of the equation for 3 and 4. I've seen it happen so many times that I kind of just try to discourage it. So I am formally discouraging you from using that version of combining resistors in parallel. Let's do some examples. So I've been talking a lot, and I know students hate when you just talk and talk and talk and you never actually do examples, because then it seems like you're not actually doing it. So I've got my trusty, I'm old, so I have my trusty HP 48, my RPN calculator. I don't know why I started using them. Some people like RPN, some people like, traditional notation. So, there's no judgment on calculators here, but mine's an HP. If you hear some weird beeps, it means I fat fingered a button on my calculator. So, but I'm working live here, so I don't have the math pre-done here. So I'm working without a wire. So if I make a mistake, it's on the internet forever. So what we're going to do is let's take this circuit and let's combine this into let's use what we know about series and parallel resistors and combine this into an equivalent resistance here. So first of all, whenever we look at this circuit, let's see, in this case, we're saying from the perspective of these terminals A, B, what's the equivalent resistance? The terminals, we're going to talk about this more later, but the whole from the perspective of these terminals is important because it changes the way we look at a circuit. Those terminals sort of add an extra branch where current can flow. So that where those terminals are sometimes mean that things that might have been in series are not actually in series, and the terminals matter. The perspective of the terminals matter. Again, we'll talk about it more. So let's look at this circuit. Let's see, do we have anything in series in this circuit? Do we have any resistors in series? So we don't. If you looked at this and you thought, oh, the 20K and the 50K, they're in series. They're not actually in series because even though they share a node, there's something else connected to that node. So there's another way for current to flow, right? So nothing is actually in series with the 20K resistor because there's more than two things that connected at that node. Okay, so but what do we have in parallel? What about things in parallel? We actually have two parallel combinations in this circuit. We have the 30 in parallel with the 60. And that's K. And we also have the 200 in parallel with the 50. Ooh. It's getting messy. Okay. And again, that's K. And now it's totally illegible. All right, so what's 30 in parallel with 60? Well, this is a common resistor combination, so I know it's 20K, but let's actually do the math. So we got all right, it's going to be the sum of the inverses of those resistors, and then whoop, we got to take the inverse of that. What do we get? Just double check here. We get 20. Okay, so what that means is that these two resistors are equivalent to a single resistor of magnitude 20K. Let's do the, what did I write here? Oh, yeah, sorry, yeah, so that was the 30 and the 60 were these. Now we have the 200 and the 50. That's going to be 1 over 200K plus 1 over 50K. I think that's 40. But let's just be sure here. Yep, 40K. Okay. Now we've done a round of simplification of combining resistors in parallel. I always like to redraw the circuit. A lot of people, they can work pretty well in their head, and I could until I was about 30 years old, and then working in my head didn't work out so well. But I always like to redraw the circuit. So I like to, if we've done a few combinations, I like to redraw it. If you take a test, I'm going to ask that you redraw the circuit. You can't just scribble out a bunch of chicken scratch and then, say, oh, here's the answer. So actually, I'm not sure how it's going to work this year. We'll see how tests go this year. That's still up in the air. But so let's redraw this circuit. So we have our terminals A and B. And now, instead of that 30 and 60, we have a 20K. And then we still have that 20K up here. And then instead of the 200 and the 50, we now have a 40K. Okay. So now looking at this new circuit that we've created, this new equivalent circuit, do we have anything in parallel in this circuit? We do not. If you said, oh, the 40 is in parallel with the 20, it's not. The 40K is not in parallel with the 20. It's drawn parallel, as in it's two parallel lines kind of a thing. But in fact, the 20 and the 40 do not share two terminals because there's another 20K resistor in between them. So we don't have anything in parallel right now in this circuit. However, the 20K is in series with the 40. So we do have the 20K in series with the 40. And what's the equivalent resistance there? It's going to be 20K plus 40, 20K plus 40K equals 60K. So we can redraw the circuit again as, I'm not going to do the AB. We can redraw this again as, instead of a 20 and a 40 now, we got 60. And back here, we still have this 20. Okay. So now we have a 20 and a 60 in parallel, and the equivalent resistance here. So if we want to make this just one equivalent resistor, that resistance, the equivalent resistance of this entire system is going to be 1 over 20K plus 1 over 60K, the negative 1. And that's 15K. So this entire combination of resistors up here could be, from the perspective of these terminals AB, this entire collection of resistors is equivalent to a single 15K resistor. So whatever you have connected to these terminals AB, it's going to feel this giant amalgam of resistors as if it's just a single 15K resistor. Oh, okay. Let's do, you know what? If we ask you to do problems like this on the homework, we might as well do them live to prove to prove they're doable. I might need an extra page in my notes. I didn't leave myself enough space to do this one. All right, let's start working our way through this. What do we got? What's in series? Do we have anything in series? I see one thing in series. I see a 35 and a 40 in series. Let's just do that. So I'm going to... So we have, this is a 75 ohm resistance. Do we have anything else in series? So technically this 10 and this 5 are in series, but it's tough to recognize that. Basically, whatever current flows through the 10 has to flow through the 5, but these are in series, but they're also in series with this big giant mess of everything. So I'm not expecting you to recognize that immediately. You will eventually, but we should recognize that eventually this whole right side of the circuit is going to reduce down to that. But for now, let's just do the 35 and the 40 as the only things that are in series. I don't see anything else in series. So what about in parallel? Without changing too much, we got this 9 and the 18 here in parallel. That's all I see in parallel right now. So we got a 9 in parallel with an 18. Hey, you know what? Let's do the thing I just told you not to do. 9 times 18 divided by 9 plus 18. Should be 6. We'll see. Look at me bragging. It should be 6. I just know it's 6. I'm trying to make up for telling you that I forgot how to multiply fractions on my SAT. And it's 6. Okay. So this is when it's really nice to have a whiteboard because you can just erase stuff and draw it in there. I'm going to work a little bit without redrawing this. Let's add a little bit more. So let's do at least one more step. So this 75 ohm resistor, which is here, now that we've found that's a 75 ohm resistor, that's actually in parallel with this 50, right? So let's do one more combination. Let's do 75 in parallel with 50. I get that's 30 is what I find. All right, now let's simplify this circuit here. So now let's redraw this as a 10, and then this, the 9 and the 18 are a 6, and then over here we had a 30 now, and a 20, and a 75, and this is getting bad. Hopefully you can still see this. It's getting rough. I'm totally going to need a new slide. Okay. All right, so what can we do now? Well, we got this 30 and this 20 that are now in series. So 30 plus 20 equals 50. And once we did that, that 50 is now in parallel with this 75, right? So 50 in parallel with 75 equals, oh yeah, we already did that. 50 in parallel. That's all right. Okay, so that combination was 30 down. So now this whole thing here is 30, and that whole thing is in series with a 10, right? So 30 plus 10, and we really should be redrawing this, but I really don't have enough space on this slide. Let's redraw it now. Let's redraw it now. Okay. What do we got? We got a 40 in parallel with a 60, right? We get 24. And you should do this on your own too. I mean, do this alongside me. So you can feel free, pause the video, go back in time, pause the video, and try to do this on your own. That's a good way to kind of go through these. But you know what? You're going to get a lot of examples of these in the homework. And if you're struggling with something, you can always go back and kind of see what I did or look at what they did in the book. Okay, so we had that 40 in parallel with the 60 here, and that was 24. And then that 24 is going to be in series with the 6 here, right? That's 30. So let's redraw this really quick. We're running out of space here, but we're almost done. Okay, now we have a 30 in parallel with a 30. That's 15. Anytime you have two resistors of the same magnitude that are in parallel, the resistance is going to be half. So it's easy to remember. So it's going to be 15, and then, so this is 15, and that is in series. So the 10 would be in series with the 15, which would be in series with the 5. So our equivalent resistance is going to be 10 plus 15 plus 5 equals 30 ohms. Okay, whew, a mess. That was a mess, but we did it. We got it. All right. Just please don't be another example. Ah, there's another example. All right, let's actually do a problem here. Let's actually do a problem. Let's actually use our equivalent resistance to solve something. Let's find the voltage across this 30 ohm resistor. So as labeled here, this V. So we have it. So now we're not just saying it's a collection of resistors. Now we're actually saying these are resistors in a circuit, and we need to combine these to find some unknown. So let's find V by, let's find this voltage by combining these into a single resistor. We know if this were a single resistor, we have a known current flowing through this mess of resistors. So if we know what that equivalent resistance of that mess is, we can just use Ohm's law to solve for this unknown voltage. So let's do that. So looking at this circuit, is there anything in parallel? No. And if you said the 30 was in parallel with the 64, you might want to go back and check. They're in parallel physically, they're physically in parallel, but circuit-wise, they do not share two terminals because there's that pesky 7.2 ohm resistor in between them. So, and the 64 is not in parallel with the 10. It looks like it's in parallel, but it's not. So we do have something in series though. What's in series? Pause the video, be honest with yourself. The 6 and the 10 are in series. So the 6 and the 10 are in series. 10 plus 6 equals 16. Oof. Okay. And then that, so this is equivalent to a 16 ohm resistor, and then that's going to be in parallel with the 64. So we could say 16 in parallel with 64 equals 1 over 16 plus 1 over 64 to the -1. 12.8. All right, so let's redraw it here. Okay. So we have a 7.2 in series with a 12.8 now. Look at that, it got clean again. It always seems nice that like we're doing it right if it comes out clean, but just because it comes out clean doesn't mean you're not also doing it wrong. Just remember that. As soon as you start to feel confident it's right, double check yourself, because sometimes you get a little too sure that it's right. Usually when people are combining resistors, here's where they always make the mistake. People make a mistake right at the last step of combining resistors. Right when they get their circuit down to where they've done all this difficult combination and they get down to like 3 resistors left and they get excited. I think they get excited, but they have 3 clean resistor values and they combine them wrong. And a lot of times if it's just 3 clean values, even if you combine them wrong, it'll come out clean. And that's always where people make the mistake. So as soon as you get to that last hurdle, where you have that last little set of resistors and they're in parallel or series, stop yourself, slow yourself down, say, wait, am I using the right equation for this? Okay. So we have a 20. Let's redraw one more time. What the heck? $30 and a 20. So what do we got? Now this is where a lot of people get excited and they'd say, oh, it's a 30 in parallel with a 20, that's 50. No, they're in parallel. So we have to do 30 in parallel with 20. And with these, usually I know the answer, but I'm still trying to I don't want to jump too far. I still want to write out the math and do the math on the calculator live with you while you're doing it. So just so we're doing an actual honest problem here, not a pre-scripted, not a magic of television, pull out that finished baked cherry pie out of the oven and say, this is what it should look like in 35 minutes. We're waiting for the oven to cook this thing. So if I burn something, you'll know. I'm sure I'll mess up one of these videos and I'll probably be too lazy to correct it in video editing. So you'll just see that big error and that's okay. There's no secrets here. You know I flubbed my SAT multiplying fraction. So there's no secrets between us anymore. All right. Oh, I left myself an extra space for this one. Why did I leave myself a blank page for this one and not the last one? Come on. I don't know. Anyway, that's done. That's it for this lecture. This is series and parallel resistors and combining resistors in series and parallel. You're going to get a lot of practice doing these on the homework, but it's fairly straightforward. The biggest thing is to remember in parallel resistors, you do the inverse of the sum of the inverses. In series, you just add them. But the biggest challenge is going to be identifying what's actually in series and what's not in series, and identifying what's actually in parallel and what's not in parallel. So that's where you got to be very careful. Okay. Oh, we're not done yet. We're not done yet. So perspective matters. So we mentioned the terminals AB. We can go back to this problem, right? We did this circuit here. We did this circuit analyzed from the perspective of the terminals AB. So I'm taking the same collection of circuits. Look at it now. So it's the same collection of circuits, but now I'm saying from the perspective of these terminals AB here. We're going to get a different equivalent resistance if we analyze this from the perspective of these terminals AB. For the sake, I haven't pre-done this, so it's probably going to come out pretty ugly, but let's do this one. Let's combine this one, find the equivalent resistance of this circuit now, and see if it's the same. So from the perspective of the terminals AB, what do we have in parallel? So we have this in parallel and this in parallel, but they're not in parallel with each other. So these are not in parallel with each other. It's just this collection and this collection. So that's what we had before. So 30K plus 60K. We know that's going to be 20K. And then we got the 200 and the 50. I think that was 40, but no, I don't trust myself. 40. So let's redraw it now. I'm going to use the space over here. So that one was a 40. And we got the 20K here. And then the 20K here. Okay. Now, from the we did that before with the last one. We combined those ones in parallel. But now look. Now, the 40K is actually in series with the 20K, right? The 40K and the 20K now share a node here and nothing else connected because we don't have a terminal connected over here. So there's nothing else connected to this node. So these are now in series. So from when we have the terminals here, when we have the perspective terminals here, now the 40 and 20 are in series. So we have 40K plus 20K equals 60K. And let's redraw that one more time. So now we have a 20K in parallel with a 60K. So we have 20K in parallel with 60K. So it's 1 over 20K plus 1 over 60K to the negative 1. And that's 15, coincidentally. So what happens when you do live. Yeah, so that's 15K. That's 15K, which was the exact value we got here. But it's only... you got to live with it. You got to live with what you got. That's what you get. That's what I get for not pre-doing the problem. Why did that work out? It worked out because this was a 20 and this was a 20K. If those had actually been different values, it would have been a different result. But the point is the analysis, when the terminals are different, the analysis is different and the result can be different. In this case, it wasn't different. So it's a terrible example, but yeah, these things happen. All right, folks, I will see you for the next lecture, part B, in chapter 3. See you next time.